We'd like to take a look at now the second part of the fundamental theorem of calculus. So far we've looked at the first part of the fundamental theorem of calculus, and that says that if you want to evaluate a definite integral of some function f of x, you can first find the antiderivative and then plug in the bounds. Plug in that top number and that bottom number and then subtract those. Okay, so we got to see a connection between integrals and derivatives to evaluate those. So just as a kind of to set the scene here, we have been defining definite integrals like this, where we take the integral from a to b of f of x dx, that's some type of number, that's this net area. Both of these numbers are constants, a and b. Right, that's how we've always been doing this. But what if we instead wanted to describe this as a function? What if we said, I don't want both of these to be constants? What if I will allow one of them to be a variable? So what we're doing is that this is still considered a net area, but let's say if I have some type of curve here, let's say this is my A, what this allows me to do is say, well, at this point, I could take this area, or because x is allowed to vary, it's a variable, I could say, what if I want to include more? But what if I want to go even further? What if I want to go even further? What if I want to be able to change where my endpoint is? I want to define that in some variable context. We could define this function like this. So if we take a look at an example, if I define this this capital F of x is going to be this thing here. This is going to be equal to sine x. Now, how we know that is because if we think about trying to apply the fundamental theorem of calculus part 1, I would take the antiderivative of cosine. This would become sine of t. I evaluate this from 0 to x. I plug in the top number first. I have sine of x minus sine of 0. So this is equal to sine x. Now this is a function. What is the derivative of this function? So the derivative of this function is going to be the derivative of sine x. That is going to be cosine, right? So if I look at f prime of x, I get cosine x. Now, what if this wasn't 0? What if this was, say, 5? Then what this becomes a 5 here. I get a 5 over here. Now this no longer goes away. Sine of 5 is some type of non-zero number. So now my function it's not just a single one. Now there's this constant floating around. But if I ask the question, what is the derivative of this? I get the same thing. Because the derivative of the constant is just going to be 0. So that leads us to the fundamental theorem of calculus part 2. If f is continuous, then if we try to have this integral defined with a variable up there, if I take the derivative of the integral, what I'm left with is just f of x. So the same thing that was inside here appears over there. That's what happened over here. When I took this integral of cosine of t dt, I did the integral, and then I reversed it by taking the derivative. You can basically think about the derivative and integrals kind of being opposites of each other, right? Because we're using anti-differentiation. So I anti-differentiate to get sine, then I differentiate to get back to cosine, and because there's just a constant down here, that derivative is going to go to 0, and all I'm left with is just plugging in that x inside here. So this is the second part of our theorem. So as an example of seeing that in a very easy one, the integral from 3 to x of this square root of t squared plus 1 dt, I find the derivative of that. If I was to try to anti-differentiate, if I was to try to take the integral of this, you couldn't do that. You don't have the skills at this point to do that. But we can still take the derivative of the integral because all we're going to do is we're going to plug in that x there. So this is going to be the square root of x squared plus 1. Pretty simple. But it's only super simple when that's an x and this is some constant. Remember, this constant, it can be anything. It could be 0, it could be 150, it doesn't matter. Now, if instead I don't just have x, I have x cubed, now I have to be careful. Because this, when I plug in, I'm going to be plugging in this variable, cosine of x cubed. However, I'm still taking a derivative. If we think about, if I have the derivative and on the inside I don't just have x, I have some type of other thing with x's, what rule do I use for the derivative? Well, we need the chain rule. So I need to multiply this by 3x squared. So I have to use the chain rule. So be careful. Some of these, when it's just an x, that's super easy because you don't need the chain rule. But once the chain rule needs to be applied, just multiply it by its derivative of this thing that you have just plugged in, and then you're good to go. So this is just the second fundamental theorem of calculus. This will not be used as much as the first part. The first part is going to be used for the rest of your calculus careers almost all the time, but this one just only gets pulled out occasionally.